thanks for coming to our seminar and welcome to today's session. We just want to remind people here in the room to please turn off or put in silent your electronic devices. For today's presentation, we have a conference titled Internal Pore Water Pressure Measurements and Effective Stress Analysis in Partially Frozen Soil. So, the thawing of permafrost is one of the major challenges facing coastal and northern communities in Canadian North, as it is associated with the deterioration of overlying infrastructure, particularly in warm permafrost regions. The near surface soils in these regions are at a partially frozen state with frozen water and ice coexisting in the pore space. If there is sufficient unfrozen water to provide a continuous water phase within the pore network, the effective stresses that control the stress, the strength and deformation of a soil should be established by a pore water pressure measurements. In this study, a new triaxial testing method is for internal pore water pressure measurements within soil was developed. Then this method was extended in partially frozen sand to measure the pore water pressure and examine the continuity of the water phase throughout the consolidated undrained triaxial test. Based on Ladanyi and Morel's concept of internal confining in frozen sand, a more Coulomb model that uses effective failure and residual frictional angles from unfrozen sand and estimate the strength of partially frozen sand was presented. The effective stresses path and critical state line of partially frozen sand were also established. So for this talk, we have our speaker, who is Yawu Liang. He is a PhD candidate in geotechnical engineering at the University of Alberta under the supervision of Dr. Nicholas Bain and Dr. D.C. Sego. He completed his master's degree in geotechnical engineering at the China University of Mining and Technology and his bachelor engineering degree in civil engineering at the China University of Geosciences. His research is focused on the internal pore water pressure measurement and mechanical behavior of partially frozen soil. So please join me to welcome our speaker.
Thanks for introducing me. I'm glad to share the research I have been working on for the last couple of years about internal pore pressure measurements and effective analysis in partial frozen soil. This is outline of this presentation. First, I will talk the background and how we initiated this research, and next I will introduce new method for the internal pore pressure measurements. Then this method was implemented into the partial frozen soil to examine the continuity in the water phase and further investigate the behavior, strength, and coexisting line in partial frozen sand. Last, I will conclude this presentation. Let me give a brief background about permafrost. Permafrost is defined as ground that remains at below 0 Celsius for at least 2 consecutive years. It annihilates about 50% of the Canada's land surface, as shown in the picture on the left. The second figure highlights the temperature, annual temperature increase between 1948 and 2016. In Northern Canada, the annual temperature has increased about 2.3 Celsius, and this trend is expected to continue in the future due to climate warming. As a consequence, the permafrost will start to thaw with the increase in the ground temperature. The thawing of permafrost is one of the major challenges facing northern and coastal communities, as it is associated with deterioration of infrastructures, such as the differential settlement of buildings and highway, and may also trigger instability of the slope. The problem is the soil in these warm regions is in a partially frozen state due to coexistent existence of the unfrozen water and the pore ice. In some situations, like the saline or ice-rich environment, there might be sufficient unfrozen water to provide a continuous water phase within the soil. Here is one example. The picture on the bottom right was taken in a freezing test on sitting sand, where the unfrozen water was turned into green color by using a fluorescent tracer. As you can see, the interconnected water channel can be found at close to -3 Celsius in this region. So in this case, the effective stress might be established by measuring the pore pressure. However, the current design method rely on the total stress approach in the warm permafrost region. But there are some challenges of conducting the effective stress in the partially frozen soil. First, how do we know if the water phase is continuous and how to examine it? In a traditional laboratory test, we only measure pore pressure at the bottom of the sample because we know for unfrozen sample, the water phase is continuous in general. So the measured pore pressure at the bottom can be representative of the whole sample, but this might not necessarily apply in the partially frozen soil because of ice. If the water phase is not continuous, the pore pressure would not be independent from other phase, and you measure pore pressure will actually be the local pore pressure. You cannot use local pore pressure to establish effective stress for the entire sample. But if we could measure pore pressure at different zones inside sample, and the continuity water phase could be examined by comparing these measurements with bottom pore pressure. So here comes another challenge. How do we measure internal pore water pressure? So the main focus study is measuring internal pore pressure and establishing effective stress in the partially soil. First, we developed a new method for the measuring internal pore pressure. Then measure pore pressure response and examine continuity water phase in the partially frozen soil. Next, to determine the effective strengths and parameters, and investigate the individual effective pore metrics on overall strengths. Last, establish a critical line. Moving on the test operators. The new triaxial operators was based on fleet-less residual parameters divided by KL. I will call it FRP for short, which includes three main components: a high sensitivity fiber optic sensor. I show you this picture. The sensor has a steel tube on top and can be easily installed by MBT fitting. Then the sensor is connected to a small diameter flex tube filled with low compressible piezometer fluid. Here we use heavy mineral oil. After injecting the oil droplet formed at tubular tube can transfer the pressure while the intimate contact between the oil and the pore water in the soil. Here we have three tubes embedded in different location sample, 8, 10, and 12 centimeters. We also have a base transducer for comparison purpose. The tests were conducted on a uniformly graded fine sand. To validate this effectiveness of this method in both contractive and dilative material, the tests were conducted on the loose and dense sand. Also, the effect of this installation of tube on the mechanical behavior of soil was also evaluated by the different test configurations with and without installation of tube. Here is this slide shows the internal pore pressure measurements in both loose and dense sand. The color line with symbol represents FRP, and FRP is like, and the dark one is for the base transducer. The orange line is for the divider stress. As you can see, all the sensors show same pore pressure response, except some difference at lower pore pressure in dense sand, which will be associated with the difference in the surface tension between the oil and the water. We know the sand has high permeability, and the water pressure adjusted relatively fast. So we expect to see the consistent measurement between the FRP and transducer. So these results confirm the effectiveness of this method. If we look at the pore pressure change at initial stage, it can be found that FRP shows the faster response than the base transducer because of the high sensitivity of the fiber optic sensor. These two figures compare the behavioral two-group tests with and without installation tube in dense and loose sand. Each group has 3 samples. The average strength of loose sample with tube is about 26 kPa higher than that of non-tube samples. In dense sand, the average residual strength with tube is around 140 higher than that of non-tube samples. As for the residual strength of loose sample and peak strength of dense sample, no significant impact was observed. So after this test, we are pretty confident this method can be implemented into the partial frozen soil. So a spiral coil was added inside the cell to control the cell temperature by circulating the water glycol. We also have a cooling plate at the base of the cell for the circulation of the liquid nitrogen. The cell temperature was monitored by 3 thermistors on the top, middle, and bottom of the cell sample surface. This is what it looks like. Unfortunately, our cell is not that transparent. The whole apparatus was set up in a freezer and insulated by a foam box surrounding the cell. This is durable for liquid nitrogen. So when I started the partial frozen test, I figured that the installed sand in our lab was adequate for the rest of tests, so it was replaced with a similar sand. There is a slight difference in the PSD, but a huge difference in the behavior, so I have to repeat some tests to ensure we have the same material in both partially and unfrozen sample. This is about the test procedures. The sample will first saturated and consolidated to a targeted effective stress, then conducted by following 5 stages. First, a rapid freezing sample by liquid nitrogen. Then the sample was maintained around -11°C. Next, the sample was warmed uniformly to -3°C. After that, examine the continuity in water phase before shear and concentration rate. This figure shows the temperature and volume change during the rapid freezing and subsequent warming. The red line here represents the volume change. About 60 millimeter water was expelled from the sample during the freezing, close to 9% of the total pore volume. 9% is the volume expansion when the water turns into the ice. So the sample was considered as completely frozen in this stage. During warming, we have 33 millimeter water was recorded to refill the sample. At the same time, the pore pressure measured from the FRP and base transducer increased and approached to the back pressure, 500 kPa. The continuity water phase was examined by increasing the back pressure and measuring corresponding increase in the pore pressure. And a continuous water phase was confirmed when all the sensors show the same response and reflect the back pressure. This table summarizes the testing program. L and D represents unfrozen loose and unfrozen dense. PL and PD indicate partially frozen loose and partially frozen dense. PL is for the frozen loose, FL. Totally, we have 3 series. First is under the unfrozen state, used as a reference. Second is under a temperature of -3°C and a concentration rate 1% per minute. The last series is about loose sand under different temperature and different strain rate. The effective confinement pressure ranges from 100 to 400 kPa. Most of the tests was under undrained condition, except for PL4 and PL4, which were tested under drained condition. Let's look at the pore pressure measurements in the partial frozen loose sand at -3°C. Again, the color line with symbol represents the FRP, documented for transducer. The right phase for the divider stress. At the first sample, 100 kPa, we didn't have the transducer. The first 2 samples utilize the same heavy mineral oil as used in unfrozen sample, but apparent hysteresis response in the pore pressure was recorded in FRP due to the high viscosity of the mineral oil at the cold temperature. For example, at 200 kPa, the FRP at 8 centimeters and 10 centimeters showed a slower response than base transducer. And at 12 centimeters, the tube was likely blocked shortly after tests. Thereafter, the piezometer fluid was replaced with a lighter mineral oil. So for the 400 kPa, the FRP at 8 centimeters matches with the base transducer. This indicates the continuity in the water phase throughout the test. But we still see the erratic measurements for the in another two tubes due to the blockage of tube. The tube was compressed following the axial deformation of the soil. So some small particles like ice or sand grains were likely blocking the tube. After tests, no shear plane was observed, but we did observe the continuous decrease in the pore pressure. So this was caused by the shear-induced dilation of the ice. In the partially frozen dense sample at -3°C, the continuity water phase was also confirmed by the consistent measurements between FRP and the transducer, particularly for the 400 kPa. And the shear plane formed during the test, similar to the unfrozen dense sample, suggesting the dilation was still caused by the soil skeleton. This table summarizes the initial and pre-shearing pore pressure coefficient p-value. Initial value was obtained after saturation. Pre-shearing p-value was measured before the shear. If we look at the sample PD1, PD2, and PD3, we can see the pre-shearing p-value was largely associated with the initial value, where the higher initial value leads to the higher pre-shearing p-value. So the temperature of the pore ice does not affect the p-value. After the pore pressure, we'll look at the behavior of partial frozen sand at -3°C. The top two figures compare the behavior of the PL and PD sand, marked by the red and dark lines, respectively. For the PL sand, it exhibits a ductile response, similar to the thinning ice. In contrast, for PD sand, it shows the stream softening, like the unfrozen sample. For the drain test, the back pressure that was open and the pore pressure was affected by not only by the dilatancy of sample, but also by the back pressure. So we observed the fluctuating the stress and the pore pressure. The bottom figure about the effective stress path. The effective stress path for PL sample converged independent of confining pressure. In PD sand, all the stress paths terminate on the same ultimate line. If we compare the stress path of PL and PD sample, they all share the same ultimate line. I will expand on this point later. Then we look at the effective strain rate and temperature on the behavior of the partially frozen loose sample. We start from left. The orange line indicates the sample test at lower strain rate, which shows the hysteresis response in both stress and pore pressure. Then we look at temperature. With the decrease in temperature, the stress increase and the pore pressure drops faster, are marked by the red lines. The dark line here also, the sample behaves more brittle at cold temperature. The dark line here represents a dense sample. As the temperature decreases, the behavior of the loose sample resembles this sample. For example, at -5°C, the PL sample shows the same similar response as PD sample at -3°C. For the stress paths, at different strain rates, they show different slopes, which reflects the strain rate dependency of the ice. On the other hand, the stress path becomes steeper at a cold temperature. For example, -10, which is considered as the frozen, so the stress path here represents the total stress path. In addition, the sample fail at different modes at different temperatures. The failure mode changes from a slight barreling at -3 Celsius to a shear plane tap at -5 Celsius to a strong barreling at -10. Okay. Next, I will talk about the internal stress, pore ice and pore pressure, and what role they play in the strength of partially frozen sand. According to Ladanyi and Morel's postulate, the soil skeleton carries the same amount of stress in frozen and unfrozen states when the soil had undergone the same stream history. The stress tensor of the ice is equal to the difference in the effective stress tensor of the unfrozen and the frozen soil. Assume this is also applied in the partial frozen sand. The diameter stress, mean stress, and the magnetic principal stress of the ice can be estimated. In pure sand, the diameter stress and the stress path show almost the same response as the entire sample. So this implies the behavior of the pure sample was mainly controlled by the ice. The sigma 3 of the ice increased until close to the cell pressure, suggesting the cell pressure was gradually taken by the ice. This also indicates the ice is under a combination of the compression and shear stress in loose sand. In PD sample, the diameter stress of ice is characterized by a linear region followed by a relative constant and stream softening regions. The stress path of ice of our sample shows the similar trends. For diameter stress, for sigma 3 of the ice, first increase up to 2% stream, then decrease to a negative value. This means in the dense sample, the ice is under a tensile and under shear stress. This slides about the relationship between the ice and the pore pressure. We know that the water cannot sustain the shear stress. So here we only compare the pore water pressure with the sigma 3 of the ice, which are marked by the green line and the blue line. The dashed line is for their difference. Often in the literature, their relationship was assumed based on thermodynamic equation. They believe their difference is remain constant under isothermal condition. But here, as you can see, their difference is not constant in both PL and PD sample. Note the sigma 3 of the ice in the dense sample decreased to almost same value as the suction from the pore water. And the summation of both is close to the matter suction from unfrozen dense sample, suggesting dilation caused by soil skeleton is shared by pore water and pore ice. The figure on the right gives the relationship in terms of incremental change. In PL sample, the incremental change of the pore ice stress is reflected by equal change in pore water pressure, as their ratio, which here is dash line, is around -1 after initial disturbance. But this is not the case in the PD sample, where the ratio is not constant. Next, these figures summarize the strength of samples. Solid line is for the partial frozen sand at -3 Celsius. The dashed line is for the unfrozen sample. Since the peak and residual strength of PL sample are close, so only the peak stress are used for comparison. It can be observed the unfrozen and partial frozen sample have similar slope but different intersection of failure lines. The slope here represents the fraction angle. Interception is for the cohesion. Again, the failure line of the PL sample have similar slope to the ultimate line of the unfrozen samples. As I mentioned earlier, the behavior of PL sample is predominated by the ice. So the soil skeleton was already at a residual state when the peak stress of sample is reached. In addition, The residual stress of PD samples are approximately equal to the peak stress of PL samples. Thus, the peak stress of the PL sample at lower strain rates are on the ultimate line of unfrozen samples, suggesting the cohesion decays via the creep. Next, we propose a model to estimate the strength of the partial set based on Ladanyi and Morel's the concepts of the internal confinement in the frozen sand and experiments above. In PL sand, the TW is the internal confinement, which is measured section from Pore-Water. The cell pressure plus TW is total effective confining pressure acting on cell skeleton. Beta, the angle beta is the effective residual angle of unfrozen sand. Cell is cohesion caused by pores. At lower strain rates, the cohesion approaches zero. So the stress can be determined by following equation. However, in PD sand, the tension caused by dilation of cell skeleton is shared by Pore-Water and pore ice, but only the tensile stress of the pore ice is considered as the internal confinement, which is equal to the measured section from Pore-Water. The alpha is the effective failure angle of the unfrozen dense sample. CD is cohesion caused by pore ice. In this figure, the solid and open symbol represents the measured and the predicted strengths respectively. As you can see, the proposed model can well reflect the measured strengths. Now we have measured pore pressure and estimated acid pressure. We are able to plot the stress distribution in a sample to understand the mechanisms involved in the strength of partial frozen sand. Here, the curve of cell skeleton is taken from the unfrozen sample, refers the strength of cell skeleton only. The S plus cell skeleton represents is measured stress from the partial frozen sand. The pore stress is represents the overall effect caused by the ice, including the ice stress and the structural hindrance, which allows the cell pressure acting on the ice transferred to the cell skeleton. So in PL sample, we have pore ice stress, soil stress, the latency of the pore ice, and the structural hindrance. In PD sample, we have similar mechanism, but the only difference is that the latency is caused by the cell skeleton. Last part is about the cordial state line. First look at unfrozen sand. Since the effective stress paths are moving towards to the cordial state, so both dense and loose sand share the same ultimate line. The condition at the end of the tests are used to plot the cell in QP space. Here, a unique cell is established in QP space. The cell in EP space was determined from 3 loose sample and undrained condition and 1 sample in drained condition. The reason why we don't use the dense sample to determine cell in EP space is that the stripling occurs in the dense sample. We have to use the local water ratio inside the shear band as the critical state water ratio. But it's very hard to determine the triaxial test. So we normally conduct a loose sand to determine the cell. This is about the cell in the partially frozen dense sand. In a similar trend we observed in the unfrozen sample, the stress paths of PL and PD sample share the same ultimate line, suggesting there is also a unique cell in QP space. The supply here is the critical state cohesion caused by the ice. There's some difference in EP space. The reason we conduct the drain test in the unfrozen sample is that it shows the contractile behavior and can expand the range of cell, but the PL sample tends to dilate without expanding the range of cell. Besides, the fluctuation in the stress and the volume change affect the determination of the critical state of water stress and water ratio. So it is suggested to carry out the undrained test only to determine the cell in the partial frozen sand. Then considering the effective strain rate and temperature on CSL. In the QP space, the CSL at -3 °C is parallel to a CSL of unfrozen sample, suggesting the temperature only affects the cohesion, not the effect of critical state fracture angle. For a sample test at lower strain rate, the critical state are on the CSL unfrozen sample. So the cohesion resulting from ice decreased to 0 at lower strain rate. Hypothetically, the CSL at -10 should also have the same slope. So that's like, so the dashed line here represents the predicted CSL at -10. It's just because the limitation of loading frame, only one sample at -10 could be finished. For a sample at -5, the critical state is close to the CSL of the at -3 °C. In the EP space, the CSL becomes steeper with decreasing temperature and increasing strain rate. Since the CSL of unfrozen and partial frozen sample have different slopes, it expects to have intersection points. So this means when the ice content decreases at a lower water ratio, the effect of ice will be minimal beyond this point, and the sample will dilate to this critical state water ratio in respect to temperature. If it's also true for a sample at -10, the CSL at -10 could be mapped with this intersection point and tested sample, which is also marked by the dashed line. Now we know to determine the behavior of the sand, not only the water ratio, but also the temperature should be taken into consideration. For example, at point A, which is in a contractile state when a sample is unfrozen, but turns into a dilative state if the sample is partially frozen. Okay, just to conclude all this we have. The validity of the continuity in water phase or partially frozen soil is a confirmation that the effective stress analysis can be carried out in a warm permafrost region. The behavior of partially frozen loose and dense sand is mainly controlled by the pore ice and soil skeleton, respectively. The strength of partially frozen sand is a function of cohesion of the pore ice and the fracture angle of the sand grains. For loose sand, the peak stress is enhanced by internal confinement and cohesion resulting from Pore-Water and the pore ice, respectively. For dense sand, only the pore ice affects the peak strength by incorporating the internal confinement and cohesion. Last, a unique CSL is established in the partially frozen sand at -3 °C. Thanks for listening.
Okay, so thanks to Yawu for this presentation. Now we have the time for question and answers. We are going to have people asking from Zoom, people asking for here. So please raise your hands so we can bring the mic in case you have a question. Any question? No question. Okay.
Thanks. No, thanks. Nice presentation here. Just for the online people, one of your slides you show that the operation sensor that is embedded in the sample shows mirror response from the work pressure that is at the base of the cell.
It means slides. In the imaging.
And from it, when you were looking at troubleshooting to define the 12 read.
Oh, sorry. To
But just what I'm asking is if many of the other sensors show some clogging or issues.
Oh,
So
I
one
know.
of them,
I understand.
and
This one, right?
yeah, that's so you don't believe in the blue and orange line, correct?
Yes.
But you believe in the green line, green dot,
Right.
the green data set.
Yeah.
So why if the what pressure response isn't the sample, you can measure outside. Why to go to the journey of putting inside the sensors?
Oh, if you look at this sample at 200 kPa, this is the base transducer. It also have chance that base transducer may have been blocked. This dark line is for base transducer. See? And if it only have one measurement, you cannot confirm if you have the if you only have one measurement at bottom, you cannot say you have the continuous water phase. You at least have 2 points to compare them. If they also show the same response, you can say, okay, the water pressure, the water phase is continuous.
Just to clarify, because I think there's a lot of rationale for having data measurements, and that's why you go to this. Then the other part that was I don't know if you covered already. How do you, especially the -10 or cold temperatures, how do you know the B value that you're measuring is just a compression of the two, or the sub 2B of the internal measurements? I know.
It means B value, right?
Yeah, like how do you know that it's just compressing the two B's like a artery, just compressing because of the lateral radial confinement.
For this B value measurements, actually, if I go back to this, if we measure the B value, we just change the back pressure, and measuring the corresponding increase in pore pressure. So in this figure, you can see my internal pore pressure with alpha P and base transducer, they show same response. So basically, all the sensor give me the same B values. So we can see the B value is actual B value, is not caused by the cubes. Because also this is pre sharing before we load. So we have same B value from all the sensor.
Thank you.
Any other question here? Any question from the chat? Okay. So thank you to Yawu for the presentation today, and we expect to see you next week. And that's all. Thank you.
Thanks for having.